Welcome to Ask and Learn.
All right, so I remember seeing this one back in the day, and I was like, what? So you're given a sphere, you're told it has a cavity, and ultimately you want to get the field inside that cavity. And so first you want to just get the field inside here and show that it can be written in this nice way, rho over 3 epsilon naught times r. So let's start with Gauss's law. So not E equals, but the flux is equal to the Q enclosed over epsilon naught. And if we do some Gaussian surface of radius r, then we can say E times pi r squared is equal to the charge enclosed over epsilon naught. The charge enclosed is going to be the total charge, so let Q be the total. Q equal total charge. And only a portion of that total charge is going to be enclosed. In particular, it's the ratio of the radius of this sphere with radius r to the radius of the full sphere, which I'll call big R. And so that's going to be, so it'll be 4/3 pi little r cubed over 4/3 pi big R cubed. And if you cancel out the 4/3 pi, you'll get this. And then if you also use the definition of density, Q is, so charge is density times volume, and then the volume, and then the volume of the sphere is 4/3 pi r cubed. So if you sub in this Q, cancel this r, oops, I almost forgot my 4 here. And then these 4s will end up canceling. You'll get the answer. You'll get that E is equal to rho over 3 epsilon naught. And it's times r in the r hat direction, which just gives you a vector r. So now I'll do this on another page. You make a cavity, and you're like, what's the field in the cavity? And you have to show that it's this constant, which is kind of interesting. That it comes out a constant, and maybe that's something that I would ponder with you if I were actually here in real life with you. But I'm trying to make these videos not too long, so but do ponder it. Maybe it'll be fun. So anyway, so basically we know that the field in without the cavity is this rho over 3 epsilon naught times r. We want to get it with the cavity. So the trick to modeling the cavity is to say that it's the same thing as taking this full sphere and superimposing on it a sphere of negative charge, right? Because the negative charges from this new sphere plus the positive charges that were already there, maybe I'll kind of draw this in, will make a cavity. And then this is my representation of the charges that were already in the sphere. And I didn't draw it this way, but they should be the same density of charges. So then we're left with the task of finding the sum of the fields from the positives and some of the fields from the negatives to model the cavity behavior. And so we already know, though, the shape of the electric field within a spherically symmetric charge distribution. And if it's negative, it's just going to be minus rho over 3 epsilon naught, but with a new coordinate system. So I'm going to call this the r prime coordinate system, where r prime refers to, I wish I had made this slightly bigger. I'm still trying to learn how to use this, how to totally predict what this, oh my God, it's really bugging out. Okay. Let's see if I can draw a circle. Okay, maybe over here is helpful. Okay. So here's my sphere. That's the same thing as this, but I drew it over here. And it's in the r prime coordinate system. But we can't have two coordinate systems, so we need to make sure these coordinate systems match. So I really believe the key to understanding this problem is having a very clear picture. Oh my God, this lag is killing me. So to have a very clear picture, I'm going to use yet another whiteboard. So here, oh, why is it doing this? Go really slow. Oh, it changes its speed. Okay. So here's one. Here's the other. And then, so we have R for some point in the middle. It's not R prime. And then we have, this is our R prime coordinate system. Let me erase the prime over here so that we're totally clear of what's going on. And then we also have a new vector that the problem introduces that I haven't introduced yet, which is the vector that connects these centers. So that's A. And then based on vector addition, tip to tail, you can say that A plus R prime equals R. So we'll kind of keep that in our back pocket. Now let's go back to getting the total field, and then we'll kind of use this fact. So if we're going to go back and mix coordinate systems, then we can say E is equal to rho over 3 epsilon naught times R minus rho over 3 epsilon naught times R prime. Right, because we're just superimposing the fields from both sources. And now notice though, this contains R minus R prime, and then we can see from this equation that R minus R prime is actually just A. So therefore it's just rho over 3 epsilon naught times A. And I'll just say again, without loss of generality, I assume the charge was positive. I think it was an assumption. Yeah, no, it was an assumption, but the problem would have worked out exactly the same if it were positive or negative. It just anchored the wording a bit better.